Welcome. In this lecture, we will discuss phases of matter, crystalline solids and diffraction, density, elasticity, tension and compression, and scaling. Matter. The four states of matter we will mention today are solid, liquid, gas, and plasma. These are the only states of matter that we'll talk about in this course. There are many other states of matter, but these are the main states of matter. To go from solid to liquid to gas to plasma, you just need to add more energy, at least simply put. Quick note, in the plasma phase, matter consists of positive ions and free electrons. I say that now because we will not have a chapter dedicated to the plasma phase, but we will have chapters dedicated to solids, which is this chapter, liquids, the next chapter, and gases, 2 chapters from now. Though we do not have a chapter where we will talk about plasma, it's important to note that even though plasma is less common to our everyday experience, it is the predominant phase of matter in the universe. The sun and other stars, as well as much of the intergalactic matter, are in the plasma phase. That said, today we will be discussing the solid phase. 2 important characteristics of solids is that they have a constant shape and a constant volume. Crystalline solids. So how were crystalline solids first discovered? Well, using X-ray diffraction. But what is X-ray diffraction and what is it used for? Well, it's used for many things, one of which was to discover the crystalline solids and to determine the structure of particular solids, not just crystalline, but originally crystalline solids. So in an X-ray diffraction experiment, a sample is placed at the center of an instrument. So let's take our instrument, at least an illustration of one, and put a sample here. And we take an X-ray tube and we take a detector, and the sample is illuminated by a beam of X-rays, and that beam is then re-emitted by the sample, which is picked up by the detector. And the X-ray tube and the detector move in synchronized fashion to hit the sample at various angles. And that signal coming from the sample into the detector is recorded and graphed. And it's graphed as an intensity versus this 2 theta, which we will get to more later. But peaks in the plot are observed related to the atomic structure of the sample in question. Most materials are made of many small crystals, like think of salt, quartz, sand on a beach, etc. But even materials that don't look like crystals to the naked eye often have underlying crystalline structure. That is, the materials are composed of a regular arrangement of atoms. Something to note is that every compound, and we talked about compounds in the previous chapter, every compound is a crystal, but not every crystal is a compound. For example, some crystals are pure elements. And as a reminder, every atom of a material, whatever the material is, of course, is composed of a nucleus surrounded by a cloud of electrons. And this is where the tale of today actually begins. Now, X-rays are high-energy light with a repeating period called the wavelength, denoted here by the Greek letter lambda. And we determine the wavelength by looking at the wave and identifying 2 identical points on that wave and then determining how far away those points are, which is shown on the slide. Now, since the wavelength of an X-ray is similar to the distance between atoms in a crystal, a special interference effect called diffraction can be used to measure the distance between the atoms of that crystal. When an X-ray encounters an atom, the energy of the X-ray is absorbed by the electrons of the atom, and the electrons take the energy and re-emit an X-ray with the same energy as the original. This is called elastic scattering. In a crystal, the repeating arrangement of atoms form distinct planes, and each atom is separated by a well-defined distance, which I've denoted here as d. When atomic planes are exposed to X-rays, X-rays are scattered by the regularly spaced atoms, and strong amplification occurs at specific angles. These specific angles are where the scattered waves constructively interfere, and this effect is called diffraction. And the angle between the incident, which is the incoming ray, which in this case would be the X-ray emitted from the X-ray tube, and the scattered beam, which is the beam going to the detector, is simply denoted as 2 theta, where theta is a Greek letter representing angle here. And why is it called 2 theta? Well, we'll get to that also in a moment. For constructive interference to occur, the scattered waves must be in alignment, meaning the second wave must travel a whole number of wavelengths more than the first. In this case, 1/2 of a wavelength is traveled on the incident side, and 1/2 is traveled on the scattered side. This adds to 1 additional wavelength. So the lower tier of wave travels a whole wavelength further than the upper tier that we see here. The exact angle at which diffraction occurs is determined by the triangle. Or again, d is the distance between the planes of the atoms of the crystal. And the diffraction angle, as I'm going to show here, is this theta, where previously we saw 2 theta, this is half of that, and so it is theta. And the relationship between the diffraction angle, the X-ray wavelength, and the distance between the atomic planes can be found using the sine function, which is something we ran across before in this course. And we can do some manipulation, and then do more manipulation to solve for the wavelength in terms of the atomic distance between the planes and the angle. Instead of just having lambda, meaning that there's 1 wavelength of a difference, what if we put n here, where n is 1, 2, 3, so we can have a 1 wavelength difference, a 2 wavelength difference, a 3 wavelength difference, indicating that diffraction occurs at whole number integer multiples of the wavelength. And this is known as Bragg's law. And Bragg's law is named after Sir William Henry Bragg and William Lawrence Bragg, which is the father-son team who won the Nobel Prize in 1915 for their work analyzing crystal structures with X-ray diffraction. All this is just to lead to the definition of a crystalline solid. It's a solid material with an orderly, repeating pattern to its structure. Crystals can be either pure elements or compounds. Conversely, amorphous solids, or an amorphous solid, is a non-crystalline solid material with atoms and molecules distributed randomly, without any order or any sort of repetitive arrangement. Now, examples of this be rubber, glass, plastic. In many amorphous solids, the constituent particles have some freedom to wander. This is evident in the elasticity of rubber and the tendency of glass to flow when subjected to stress over long periods of time. You can see this in very old windows. They are thicker at the bottom than they are at the top because glass is slowly, very slowly flowing downward under the effect of the body force or gravity. Density. Let's start with the question. Is gold heavier than paper? Now, this question is ambiguous because it depends on the amounts of gold and paper. A stack of paper is heavier than a gold ring, but a bar of gold is heavier than a single sheet of paper. So this question really doesn't make sense. A better question would be, is gold denser than paper? And the answer to that is yes. The masses of atoms and the spacing between them determine the density of a material. So what is this density? Well, density is just the measure of compactness of a substance, the amount of mass occupying a given volume or space. And it's denoted by this Greek letter rho. That's not a P, that's a Greek letter rho, which equals m/v. And density is a property of a material. It doesn't matter how much of the material you have. For example, a pure iron nail has the same density as a pure iron frying pan. They have different mass, weight, volume, etc., but mass density will be the same so long as both are at the same temperature and pressure. When a loaf of bread is squeezed, the volume of that bread decreases and the density goes up because the mass is constant. And we see that if we go back to our definition of density, density equals mass over volume. So if I decrease the volume, I have to therefore increase the density. And we'll look at this in more detail now. Consider a plot of density versus volume, and then consider some volume V, and consider that within this volume there's some mass. And we're going to be looking at what happens to the density when we change the volume while keeping the mass within the volume constant. So in its current state, we see that density has some value corresponding to the current volume and mass. If we increase the volume but keep the mass the same, we get a new density value as displayed on the plot. If I increase the volume again, we get another value on the plot. And again, another value on the plot. And one more time, we get another value on the plot. And what we see is that density is inversely proportional to the volume. As volume increases, density decreases, and vice versa, assuming the mass is constant. Let's change things up a bit. Let's now plot density versus mass, assuming we keep a constant volume. So in the current state, we have some density as a function of the mass. If I increase the mass inside the volume, we get a new point on the plot. If I increase the mass again, we get another point on the plot. Again, another point, and again, another point. And so what's the trend here? We see that density is directly proportional to the mass. Increasing the mass increases the density, assuming the volume is held constant. Elasticity. Consider a helical spring. When a force is applied downward, the spring compresses. When a force is applied upward, the spring stretches. These are known as deforming forces because it deforms the object. So whatever force has been applied to the spring in the example shown, that particular force, whatever it is, can be considered a deforming force. This leads us to elasticity. It's a measure of how much an object, 1, changes when a deforming force is exerted on it, and 2, returns to its original shape after the force is removed. Materials that require more force to stretch or compress are more elastic. Materials that do not return to their original shape after a force is removed, such as clay, putty, dough, etc., are considered inelastic materials. Problem 1. If we consider two materials, steel and rubber, which is more elastic? A, steel, B, rubber, C, they're equally elastic, or D, not enough information? The answer is steel. Why? It takes more force to stretch a steel wire than to stretch a rubber band. Also, steel regains its original shape much quicker than rubber after the force is removed. And so we conclude that steel is actually considered to be more elastic based on the previous slide's definition of elasticity. Hooke's law. Let's make a plot of force versus the deformation amount. Hooke's law is a description of the relationship between a deforming force and the extent of deformation. So in this particular example, we're going to be looking at a spring. So let's look at a spring, and there's a force applied to the spring due to the mass hanger attached to the spring. Now we're going to be looking at here the force the spring applies in order to maintain an equilibrium state. This will be our reference vertical position. So let's say we add weight to the mass hanger. The spring therefore stretches some distance downward. So there is a deformation. In response, the spring actually has an upward force because it has to keep the mass here. So the downward force of gravity on the mass is greater here than in the first example, and therefore the spring force must grow. And what we see is that the spring force increases as the deformation increases. And we'll see more of a trend as we go to the next example here. Let's say the spring stretches more in response to a greater mass on the mass hanger. The spring stretches more. To be in equilibrium, it must therefore apply a greater force to hold the mass here. And so we see that, again, another point is placed on the plot. And we do the same thing again. Spring is deformed more, and therefore it applies a greater force. Another point goes on our plot. And again, more deformation, stronger force due to the requirement that it's holding this mass here, and we get another point on our plot. What's the trend? Well, the trend is that the spring force is proportional to the amount of the displacement, or the deformation. And this is what Hooke's law states. Hooke's law, the extension of a spring is directly proportional to the force applied to it. Fs is our spring force. K is a spring constant which depends on the geometry of the spring, and delta y is our displacement. It could be delta x, delta y, whatever, as long as whatever symbol goes here is representing the stretch or compression of a spring. And don't get confused by the negative sign. The negative sign is simply indicating the spring force is a restoring force, in that the force applied by the spring is in the opposite direction to the displacement or the extension or compression of the spring. As we saw in the previous slide, the spring was deformed downward and the force was upward. So the force is in the opposite direction of the deformation. That is what the negative sign indicates here. Tension and compression. Tension causes things to get longer and thinner. Compression causes things to get shorter and wider. For the girder shown, tension is on the upper side and compression is on the lower side, because on the top, the particles are pulled further apart. On the bottom of the girder, the particles are shoved closer together. But what is this red dotted line? That is the neutral layer, a region that is neither stretched nor compressed. Let's flip things around a bit. Now we put a block on top of a girder which is held in place by two pegs. Compression occurs at the top of the girder, and tension occurs at the bottom of the girder. Because, again, compression is where the particles are shoved together, which occurs at the top, and tension is where the particles are pulled apart, which occurs at the bottom of the girder. And again, we have this neutral layer, where particles are either pulled apart or pushed together. This is an I-beam. An I-beam is used in construction. It's essentially a solid bar with some steel scooped from its middle where it is needed least. The beam is therefore lighter for nearly the same strength. And what does that even mean? Well, here we have flanges, and this thing here is called the web. Now, the stress placed on these I-beams is predominantly in the top and bottom flanges when the beam is used horizontally in construction. One flange is stretched while the other is compressed. But the web is a region of low stress because it's near the neutral layer, and this simply holds the top and bottom flanges apart, holds them together and apart from one another. Now, heavier loads are supported by the flanges, and very minimal stress is placed on the web because it's near the neutral layer. Problem 2. If you make a hole horizontally through the tree branch, what location weakens the branch the least? The top, the middle, or the bottom? Well, the middle. Why? Because the middle is where the neutral layer is. So the least amount of stress is placed there by the weight of the branch on itself. It weakens the branch the least. Fibers in the top part of the branch are stretched and fibers in the lower part are compressed, but again, in the neutral layer, the whole will not affect the strength of the branch. Scaling. Consider an elephant and an ant. Ants, as we know, are strong for their size. If an ant were scaled up to the size of an elephant, would it be stronger than the elephant? The answer is actually no. Such an ant would barely be able to lift its own weight. But why is that? As the size of an object increases, it grows heavier faster than it grows stronger. This leads us to the definition of scaling. The study of how shape and size and volume of any object relate to its strength and weight. Strength is related to the area of the cross-section. Weight is related to the volume. Let's take a simple example of a cube, where each dimension of the cube, by definition, is the same. So they all have some initial length Li. The area initially, then, is simply Li squared. And the volume initially is therefore Li cubed. But what if we triple the dimension, such that the new dimensions are 3 times the initial dimensions? The area in this final scenario therefore becomes 9 times the initial area. So I tripled the dimensions, and the area becomes 9 times its initial. What about the volume? It becomes 27 times the initial volume. Now, why does this matter? Well, as mentioned on the previous slide, if the strength of an object corresponds to the area and the weight corresponds to the volume, we can see here that the weight increases more rapidly than strength for a proportional increase in dimension. So the bigger something gets, the more difficult it will be for that thing to support itself because its weight increases faster than its own strength. In summary, we talked briefly about phases of matter, crystalline solids and diffraction, density, elasticity, tension and compression, and scaling. I'll see you next time.